Okay, so in this subtopic we will look at two irreducibility tests. Okay, basically we are going to work in QX. Okay, two irreducibility tests. So these tests will give us some methods of trying to show that polynomials are irreducible. Okay. So the first one is called as the mod P test. Okay, now we know that ZP is a finite field. Okay, so if I can, it is easier to talk about irreducibility in ZP compared to Q, because ZP is finite. So doing things in finite fields is a lot simpler. So this is essentially going to give us a method to say that a polynomial is if a polynomial is irreducible in ZP, then the corresponding polynomial will be irreducible in Z, okay, or in Q. Again, here I think we are looking at Z. Okay, so the mod P test. Mod P test. Okay, so test is very simple. So again, by this polynomial, okay, what I will mean is the polynomial attained by reducing each of the coefficients down mod P. Okay, so that's what we are going to look for. So let f of x be some polynomial in Z, polynomial over Z, and P be some prime. Okay. We'll keep the degree of f of x to be greater than or equal to 1. If so there are two conditions which need to be satisfied. Okay, again I'm not writing what this is. This is the polynomial attained from f by reducing each of the coefficients down modulo p. Okay, so in the notes it's written, but I'm not writing here. So if one, in fact, there are two conditions that you need to check. One is if fx bar is irreducible in ZPX, and two, see what happens when I reduce each of the coefficients down mod P. Okay, so it is possible that the degree of the polynomial drops, right? Example, if the highest degree polynomial is a multiple, not example, actually that's the only way, when the highest degree coefficient is of is a multiple of P, right? And when I reduce it down modulo P, it will, that highest degree coefficient will become 0, right? So the degree is going to drop. There's no way the degree can go up, right? It can only go down in that manner. So if the degree of my fx is the same as the degree of fy, that means, in other words, the highest coefficient of f, okay, the leading coefficient of f is not a multiple of p. Okay, so there are two things which you need to check. Okay, so if this happens and this happens, then f of x will be reducible in Z, and f of x is reducible is irreducible. If it is, yeah. Okay, so the proof is simple. We are going to use prove the contrapositive, in fact. Okay, see, we have this statement implies this statement. Okay, so it is enough for me to show that not this statement, right, not this statement implies not that statement. Okay, so it is enough if we show that if f of x is reducible, then f prime of x, f of x bar is reducible, right? Here we have, if this is irreducible, then this is irreducible, okay? In fact, yeah, that's what you would do. So let's assume that this is reducible, and in fact we'll get a contradiction which says that this is reducible, okay? So suppose f of x is reducible in zx. What does this mean? This means that we can find two polynomials in zx. I think there is one small I'm sorry. This is not q, this is in q. Okay. That you have to be a little careful. It's if it's not a maybe it could have a content greater than 1, then you're in trouble. Okay. So suppose this is reducible in qx, then what happens? We know by the Gauss lemma that if it's reducible in q, then it is also reducible in z, right? If I can break it down into two polynomials in q, I can also break it as a product of two polynomials in z. And those two polynomials which I break down into, none of them are going to be constant polynomials, because if you look at the proof in Gauss of the Gauss lemma, that f and f1 and g1, whatever we have taken over there is no change in degree. Look through the entire proof, there will never be a change in degree anyway. Okay, so that would happen. So this will mean that f of x is reducible, or let me put it this way, is so there exists g of x and h of x in zx of degrees greater than or equal to 1, such that f of x can be written as g of x times h of x. Let me try to tell you exactly what I have done here. See, since it's reducible over q, you can write it as a product of some g1 and h1 in q, right? Then you do that manipulation, how we have done in the proof of the Gauss lemma, that is, multiply by the LCM of the denominators and do all of that, whatever you have to do, and you will get two polynomials of the same degree. But here you started with polynomials of degree greater than or equal to 1, right? Because these were, it's reducible here. Reducible here means what? You find non-unit polynomials, that means degree greater than or equal to, these are both going to be of degree greater than or equal to 1, okay, such that this happens. I need to have their coefficients from z, otherwise I am going to be in trouble. Okay, so what happens here? We know that this is a homomorphism from, right, a usual homomorphism from z to zp, that is reducing modulo p, that extends to a homomorphism from zx to zpx, right, which takes each polynomial in zx to the polynomial in zpx, that is attained by reducing each of the coefficients down modulo p. It's a homomorphism. That's what I need to know here. That means if I look at this polynomial that is reducing each of the coefficients down modulo p in f, right, it will essentially just be reduce the coefficients down in g modulo p, right, and then take the product with reduce the polynomials down here with modulo p. Okay, now we should ask ourselves a question. So it looks like I have broken it down into a product of two polynomials. Only problem is that I should be sure that none of these, because we want to show it's reducible in zp, right? So none of these can be constant. We should be sure that none of these are constant, because then it would be a unit. right? So how would I be sure that it's not a constant? Can anyone see it? Yeah? But how do you know that the degrees of G bar and H bar are the same degrees as G and H? We know that the degree of F bar and F is the same. How do you know that the degree of G and G bar is the same? When I take bar, the degree need not always remain the same, right? If I take bar, the degree need not remain the same. How do you know that the degree of G and G bar is the same? Yeah? Because? The product of the degree? So? Yeah? Okay, so in case this degree falls, okay, if this degree falls, then what will happen is, we know that the degree of this is the same as the degree of F, right? And the degree of this, which is the degree of F, is equal to the degree of this plus the degree of this. So if any one of them have degrees strictly less than these degrees, it will become strictly less than the degree of G plus the degree of H, which is the degree of F. Essentially saying that the degree of F is strictly less than the degree of F, which gives us a contradiction. Okay, so suppose the degree of G of X was strictly less than the degree of G of X, or the degree of H bar of X. Okay, in either of these two cases, it doesn't matter. Okay, then what would happen is, the degree of F, I'm trying to be, would be the same as the degree of F bar, okay, which is essentially the degree of, because we are working in an integral domain, ZP is an integral domain, so this is degree of G of X bar. Okay, but if either of these two hold, it doesn't matter which one, if any one of them hold, because we know that the degree of this has to be less than or equal to the degree here. When I go reduce modulo P, the degree cannot be higher, right? So if any of this strict inequality holds, then this will definitely be less than the degree of G plus the degree of H, which is nothing but the degree of F. So this is a contradiction. Okay, this is a contradiction, and therefore what happens is, I am contradicting this statement. What does it mean to contradict this statement? That means the degrees have to be equal. Okay, greater than or equal to, but then the greater cannot happen ever. When I reduce modulo P, no greater than degree. Okay, so therefore the degree of G of X, G bar is equal to the degree of G of X, and the degree of H bar is equal to the degree of H of X. Okay, but both these degrees are greater than or equal to 1. So hence these degrees are also greater than or equal to 1, which means they are non-units. Okay, these are non-units, and therefore these are both non-units because these degrees are greater than or equal to 1. Okay, in Fx we know what the units are. Zp is a field, right? So the only units are constant polynomials, non-zero constant polynomials. That's the only units. So therefore f of x bar is reducible. Okay, this contradicts this assumption that it's irreducible, right? And therefore this has to be false. If this has to be false, means this cannot be reducible. And anyway, we know that this cannot be a unit because this degree is the same as the degree of f bar, so it has to be irreducible. Okay, so therefore, which is a contradiction, which contradicts the assumption and therefore f of x is irreducible. So this is called as the mod p test. Let's look at two small problems which you can, of course, people could ask many problems like this, but let's look at two small problems with this. How would you utilize this? Right. So I'll give you one again. Of course, I'm only doing problems in Z2, but you could use Z3, Z4. The way you would make your choices is, I mean, there are always infinitely many choices of p that you could take in these problems. So, yeah, that is, how do you choose is a little bit of a, how do you choose which p to use is a question. Okay. Generally, you definitely know which p's you cannot use, that is all the prime devices, the first one you cannot use. Okay. Other than that, which p's to use, I think there is a trick to it, but I don't want to say that. Okay, anyway, so one is, so show that the following polynomials are irreducible in Zx. Okay, Zx or Qx, it doesn't matter because these polynomials which I'm giving you are primitive. Okay, or let us put Qx, why not? So 1, 21x cube minus 3x square plus 2x plus 9. So we know one thing, since this is a polynomial of degree 3, it is reducible if and only if it has a root, right? So it is reducible if and only if it has a root. Okay, so let us go modulo 2. Okay, that's very easy to see. So going modulo 2, what we have is, so let's you take f of x to be 21x cube minus 3x square. Okay, so reducing f of x modulo 2, we get f of x bar equals, what do we get? 21 will be 1, right, x cube. So minus, let's go with plus, right, minus 3 is also 1 modulo 2. Why you want minuses? 0, 1. So all you've got to check, now you've got to check whether this is reducible or whether this is irreducible in Z2. You've got to check whether this is irreducible in Z2, right? How do you check whether this is irreducible in Z2? You just need to check whether it has a root in Z2. Does this have a root in Z2? No. Now to check that it has a root, you just got to check 2 points, 0 and 1. If you evaluate at 0, you get 1. So 0 is not a root, right? 1 is also not a root, because if you substitute 1, you get 1, right? You are going modulo 2, so you get 1. Okay, so notice that f of 0 equals 1, and okay, I'll specify here in Z2x. Okay, so I have to substitute and then you have to go modulo 2. You have to go modulo 2. Right? If you put 1 over here in Z, you're going to get 3, but modulo 2 you're getting 1. Okay, so therefore f of x bar has no roots no roots in Z2 and is of degree 3, which means that f of x is going to be irreducible in Z2. Has no roots in Z2 and it's of degree 3, right? Polynomial of degree 3 or 2, I just need to check whether they have roots. Okay, so therefore f of x, in fact actually, no, I will not tell you that. Okay, so f of x is irreducible in Z2, which means that f of x is irreducible in Q. Okay, so that's one. Let's look at another case. See, if I give you a polynomial in Q, okay, multiplying a non-zero C to it will not change its reducibility and irreducibility. Can everyone see that? Multiplying some C to it, right, multiplying a constant will not change its reducibility and irreducibility. Can everyone see that? So essentially what I am telling you is that if C is positive, okay, then f of x in Qx is reducible if and only if C times f of x is reducible. Can you see that? Yeah? I didn't get you. Where prime? Prime? By the previous theorem, no? We are using the previous theorem. Mod P test is only for primes. ZP is a field. Zns are not fields. A full argument would not work. Zn generally is not a field. Only ZPs are fields. Only when n is a prime, ZP is a field. Nothing in our argument would work in the previous theorem if P was not a prime. If you look through the entire argument, we have used in multiple places that it is a integral domain. Okay, ZPX is an integral domain, which would not hold if it was not a prime. Okay, so you have to go with this. You have to go with primes. Of course, why you choose 2 and not something else, frankly, I cannot ask you. I cannot answer. You can try with other primes, it might work, it might not work. Okay. Two primes definitely you cannot try with. Which ones? 3 and 7, right? Because this is a multiple of 3 and 7. So if you go modulo 3 or 7, then you could try with 5 and C. I don't know. In 5 you would get x3 plus, check that, plus 2x square plus 2x plus 4. But then again you would just need to check for roots. But you would have to check for 5 instead of 2. Right? In Z5, if you use 5, you would have to check for 5. I don't know whether it would work or not. I don't want to say anything. Okay, so this is reducible if and only if C times f of x is reducible. How do you think of this? This is quite obvious. If f of x is reducible, that means you can write f of x as some g of x times h of x. Hence C times f of x you can write as C times g of x into h of x. So therefore this will be reducible. Again, suppose this is reducible, that means C times f of x can be written as g of x times h of x. Then you can write f of x as 1 over C times g of x times h of x. So therefore that will be reducible. So that's pretty obvious that this holds. So the reason I am telling you this is we could use this even in other cases. Hence this is in fact the reason why you need not work much in Qx with polynomials over Q. You could just work with polynomials over Z. Okay, so So what about the reducibility and irreducibility of this polynomial? That is 3 by 7 x raised to 4. So slightly different trick. Minus 2 by 7 x square plus 9 by 35 x plus 3 by 5. Okay, so showing that this is reducible is equivalent to showing that any constant multiple of this. So what should I multiply? 35, the LCM of the denominators. That's the natural choice. Okay, so multiply by that. So let's take consider f of x to be, I'm just going to multiply by 35. When we multiply this throughout by 35, what do we get? Here we would get 5, so 15x raised to 4, right? 15x raised to 4 minus 10x square plus 9x plus 3. Okay? I made a mistake. Oh, thank you. Here we have 21. Okay? Again, I am going to go modulo 2 only. This is again I am going to go with go modulo 2. This is not a polynomial of degree. Here you cannot go 3 and 5 because this is 15. It would reduce the degree. Okay? Yeah. So yes. So this is a polynomial of degree 4. Okay. So you cannot just check for roots. You have to actually check that it doesn't reduce in the this thing of, anyway, let's see how it works. It's still 4 is still easy enough to work. There are some tricks you could utilize. So so reduce f of x modulo 2, we get, what do we get? F of x bar equals x raised to 4. This fellow will become 0, okay, plus x plus 1. Okay, just keep this polynomial in mind. I will come back to this polynomial later. Okay, I'll tell you why, but keep this polynomial in mind. I'll come back to it. So I want to show that this polynomial is irreducible over Z2. See, to reduce a polynomial in to reduce a polynomial down in to reduce a polynomial of degree 4 as a product of two polynomials, you have only two options. Either it is going to be a polynomial of degree 1 into a polynomial of degree 3, right, or 2 and 2. If you can reduce it as polynomial of degree 1 into polynomial of degree 3, it means that it has a root. Correct? So first let us show that it cannot be reduced as polynomial of degree 1 into polynomial of degree 3. How? Just showing that it has no root. Does this have a root? No. Just check 0 and 1. 0 is not a root, right? Substitute 0, you get 1. Substitute 1, you get 1. So no 0 means it cannot be reduced as polynomial of degree 1 into polynomial of degree 3. So if it can be reduced, it has to be reduced as polynomial of degree 2 into polynomial of degree 2, which means that, okay, if it can be reduced as a polynomial of degree 2 into polynomial of degree 2, that means a polynomial of degree 2 should divide it. Okay, let's see what that tells us. Okay, so suppose f of x bar is reducible in Z2x. Okay, you have two cases. Case 1, okay, one is some x minus or some x plus a. Let me put minus. I think I would be okay. Let's go with plus. Okay, some x plus a divides f of x. This is the first case. That is, some x plus a divides f of x, which would then mean that f of minus a, okay, for a in Z2. Okay, see, because, okay, I think let me go a little slower. So there exists a polynomial of degree 1, say x or ax plus b, and a polynomial of degree 3, say g of x, such that we can write f of x as, or f of x bar as, this a and b come from Z2. Okay, so a and b are either 1 or 2. Of course, a is actually only possibility is 1. Why? Because I want a polynomial of degree 1, right? The only possibility for a is, a can only be 1, the coefficient of x, because we are working in Z2. Okay, and I want a polynomial of degree 1 here. Okay, so this can be written as x plus a times g of x bar. But what will this mean? This will mean that f of x, f of b bar, right, f of b, because b and minus b is the same thing in Z2. Okay, would be b plus b g of b bar, which is 0. Why is this 0? Because 2b is a multiple of 2, right? So you're going to get 0 there. Okay, so this is 0. So can this take place for any b in this thing? But notice here that your f of 0 bar, right, is 1, which is also f of 1 bar. So it has no roots. Okay, so therefore b is a root of f of x bar in Z2. Okay, so this is a contradiction because it has no roots. Okay, the second possibility is you can break f as product of two polynomials of degree 2. Okay, so let's see. So the second one is there exists, or in other words, let me put it directly, there is a polynomial of degree 2 which divides it. Okay, so there exists some, let me not write ax square because this can only take the value 1. I want a polynomial of degree 2, right, plus ax plus b in Z2x such that x square plus ax plus b divides f of x bar. So that means this a and b are in Z2. Okay, a and b are in Z2. Let's just take different possible values for a and b. Okay, so how I'm going to make this argument is like this. I'm going to basically show that all these type of polynomials have roots, but this has no roots, because every root of this is a root of that. Okay, so let's see, or I think I might need to do more than that. I think that might not work. Okay, in any case, let's see. So let's go with the flow and see. So obviously b cannot be 0, right? Why b cannot be 0? Can anyone tell me? What would happen if b is 0? Yeah, so if b is equal to 0, what happens? 1 is a root. Sorry, 0 is a root. If b is equal to 0, that means 0 is a root of this polynomial, right? X divides this polynomial, so x would also have to divide this. I mean 0 is a root of this, but that's not possible because 0 is not a root of this. Right, I am using the remainder theorem. Okay, so if b is equal to 0, then what would happen is x square plus ax would divide f of x bar. Okay, but we already know that x divides x square plus a square, right? You can write x square plus ax as x times x plus a, right? So therefore this divides this, and this will imply that x would have to divide f of x bar, okay, which would mean that if x divides something, 0 should be a root of it, okay, which means that f of 0 bar would have to be 0. It's a contradiction. Why? Because f of 0 bar is, what is f of 0 bar? 1. So this is a contradiction. X cannot divide that. So b cannot be 0. So therefore b has to be, it has no other option, it has to be 1. Okay. So b is 1. Now we have only two more, we have only two options for a. Either a is 0, right, or a is 1. So one of those cases are very easy. If a is 0, a is equal to 0. If a is 0, what happens? B we know is already 1, right? So you put a equals 0, what do you get? X square plus 1 should divide f of x bar. Can anyone get the contradiction in this? Yeah? That's right. So you can see, can everyone see it? Does this polynomial have a root in Z2? No? 1 is a root, right? If you substitute x equals 1 in this, you get 0. So 1 is a root of this. So that would have to mean that 1 is a root of this also. That's not possible, right? Because I mean this divides this, so you can write this as this times some other polynomial. Therefore, if this has a root, it has to be a root of this. Okay? So this would mean that, okay, let me write it like this. There exists some g of x bar in Z2x such that f of x bar would be equal to x square plus 1 times g of x bar. This would mean that f of 1 bar would be, this is 2, so you get 0. This is again a contradiction, as f of 1 bar is 1. Okay, so this is not possible. So the only possibility is a has to be 1. So therefore, in fact, let me write here. Suppose, therefore, a has to be nothing but 1. So we have landed up with proving that a and b, if this divides this, a and b should be 1. Okay. Okay, we can't do the same argument here because this has no roots in Z2. Okay, x square plus, but what has happened here? Okay, so therefore, now it's quite easy to see it. Okay, so therefore, a is equal to 1 and b is equal to 1. So therefore, you can find a polynomial. Okay, you can find a polynomial. Let me call it as h of x. Such that f of x bar is equal to x square plus x plus 1 times h of x bar. Now what happens? Exactly. This should be the same polynomial. Can you tell us why? Because what is the degree of this polynomial? 2. Right? The degree of this polynomial is also 2. That means again it has to be of this type of a form, which means it divides f of x bar. You make the same argument again, you will see that this has to be the same as this. Now you just take the product and check. Okay, but what we know is that the degree of this, that is 2, which is the degree of this, is 2 plus 2, 2 plus the degree of h of x bar. Okay, so therefore, what have I done? 4. Right? Yeah, this is degree 4, right? So therefore, the degree of h of x bar should be 2. Okay, and therefore there is no other option for h of x bar also. This also has to be x square plus x plus 1. Okay. Now you take the product and you check whether you are getting the same polynomial. If you don't get the same polynomial, it means you have done some mistake. This in fact tells us something little more than that. Let's see who can think of it. So therefore, so f of x bar would be x square plus x plus 1 into x square plus x plus 1. What is this? Let's take the product. You get x raised to 4 plus, what is the coefficient of x square? It will be x square. So 3x square, right? That's it. 3x square. 3x square is 1x square, right? What did I start with? What was my f of x bar? Can anyone tell me? I can't recollect. Yeah? Plus x square. No, plus x plus 1. No x square. Okay, so that itself tells us that this thing. So this is x square plus, what is this thing of x? 2x, so 0. Right? Coefficient of x would be only in this way, x times 1 plus x times 1, that is 2x, 0 and 1. Okay, so this is not the same as, this is obviously not the same as f of x, because your f of x bar, as you all have told me, is x raised to 4 plus x plus 1, but this is x raised to 4 plus x square plus 1. Okay, so this is not the same. Is this polynomial reducible in z to x? Yes, you can break it down as the product of these two polynomials. Okay, but this one is not. Yes, you can actually tell what are all the reducible and irreducible polynomials of degree 4 in z to x through this proof, if you look at it properly. Okay, so that's a nice one. Okay, and finally, one of the most important results in this section is the Eisensteins criteria. Okay, this gives a very nice technique for getting the and you have no infinite choices here of the primes. There are only finitely many choices of primes. So it works by the Eisensteins criteria, but it's not a. These are only methods of. It is. They are not. What do you call them? Equivalent statements. This is only one direction. If this property holds, then it is irreducible. Otherwise, we can't say anything. Okay, so this is called as the Eisensteins criteria. So suppose we have a polynomial f of x equals a n x raised to n plus a n minus 1 x raised to n minus 1 plus up to a1x plus a0 in zx, and p is some prime. Okay, if p is some prime such that, so you have two conditions that need to be satisfied. One is, see, these coefficients come from z. Okay, I want to talk about irreducibility over Q. So that this property, these two properties is what you need to check. One is, firstly, P does not divide the highest degree. So P does not divide an. Okay, but P divides everything else. Okay, and secondly, you should just write it like this otherwise. Okay, it divides all of these, and 2, P does not divide an, and P P divides A square, A naught, but P square does not divide A naught. Okay. P divides A naught, but P square doesn't divide A naught. Okay. Then f of x is irreducible in Qx. Okay. So again, so for the proof we are going to do the same. Yeah. So we assume that f of x is reducible in Qx and get a contradiction. Okay. So suppose f of x is reducible in Qx. Okay. Again, as I have told you, that now you can break it down into two polynomials in Q. Okay. But by the Gauss lemma, okay, in fact by the proof of the Gauss lemma, you can actually get the polynomials in Z of the same degrees as, so you are going to get polynomials of degrees greater than or equal to 1. This is essential. Okay. So this will mean that you can find g of x and h of x in Z such that the degrees of these g of x and h of x is greater than or equal to 1. Okay. I hope this is clear as to why I can get this. This is using the proof of the Gauss lemma. Okay. Because if you go through the proof, you see that the degrees do not change. As we manipulate, the degrees don't change. So that is important. Okay. So this means that, yeah, so the degree of g of x and h of x is greater than or equal to 1, and f of x can be written as g of x times h of x. Okay, let's say that the degree of this is t and the degree of this is s. Let me go with the same notation. Okay, in fact I'll go with p and q, just because. Okay, so we'll say that p of x is some at x raised to t plus up to a naught. Alright, just where your at is non-zero, that means this is of degree t. Okay, and we'll take q of x, oh sorry, I can't use a, right? So we'll use b, and we'll take q of x to be cs x raised to s plus up to c naught, where your cs is non-zero. So therefore this polynomial is of degree s. Okay, so your n, okay, n will be, yeah, n will be t plus s, correct? The degree of f will be t plus s. Okay, so let's see what we have here. So what does this tell us? So one, p does not divide an. Okay, since p doesn't divide an, what is an? Can anyone see? Yeah, an will be bt into cs, right? So as p does not divide an and an is equal to bt into cs, what happens? Okay, this will mean that p does not divide bt into cs, and if P doesn't divide Bt into Cs, it cannot divide either of them, right? So P will not divide Bt and P will not divide Cs. In fact, one of them is what we actually require. Okay. Also, we know that P square doesn't divide A naught. Okay, so see what happens here. So your A naught is equal to B naught into C naught. Okay. Now we know that P divides one of them. We know that P divides A naught, right? We know that P divides A naught, which means that it has to divide either B naught or C naught. P divides A naught, right? Since P divides A naught, it has to either divide B naught or C naught. But we know that P square doesn't divide A naught, which means that P cannot divide both A naught and C naught. Okay. So as P divides A naught and P square does not divide A naught, P divides exactly one of B naught or C naught. Okay, so we will say let P divide B naught. It doesn't make a difference to our this thing which side we use, because everything looks symmetric. So P divides, we'll say that P divides B naught and P does not divide C naught. Let me just go with the same choice. Yeah, that's fine. Okay, so P divides B naught, but it doesn't divide Bt. Okay. So we have this. So P doesn't divide. So P divides B naught, but it doesn't divide Bt. The last one it doesn't divide. We are going to take the smallest integer for which P doesn't divide, Br. See, take the smallest one, the first. So P might divide B naught, it might divide B1, it might divide, but at some stage it's not going to divide. The first one you need to take. The first one which it doesn't divide is what you need to take. Okay? Is that okay? See, P divides B naught, right? But it doesn't divide Bt. It divides this, it doesn't divide this. Keep going to your right to find the smallest one which it divides, or start from this side. P divides this. Keep going to your left and check which is the last one that it divides. Somewhere it will stop, because this one it doesn't divide. Worst case scenario, you will be at Bt. Okay, so we'll take R to be the minimum of all the I in 1, or in fact 1, 2 is sufficient, right? 1, 2 up to T, such that P doesn't divide Bi. Is this okay? Smallest one, smallest index for which P doesn't divide Bi. What is that? Br. Is this okay? You keep going from here to your left and check the first time it becomes P doesn't divide the coefficient. Okay. So therefore, P will not divide Br. So now is the beautiful argument. You have to look at AR. Okay. What is AR? AR will be, what is AR going to be? It is going to be BR times the Cauchy product, right? So AR, the coefficient of x raised to r, will be BR times C naught plus, right, Cauchy product, plus BR minus 1 C1, BR minus 2 C2 up to B1 CR minus 1 Okay. Now notice here that P divides AR. Why? Yeah, because P divides all of this thing except for AN. So why is R not? That's fine. That is quite clear, that because this number is the degree of this is definitely less than n. Okay, the degree of this is definitely less than n, so that's fine. So this is not an, because the degree of this polynomial is definitely less than n, right? Otherwise this would be constant. So the degree of this, so therefore and this R is less than t, so obviously this is going to be less than n. Okay, so this is not an, so P has to divide this. Now what we have done, we have taken this to be the first time it doesn't divide, so therefore it's going to divide all of these, right? It has to divide this, 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 and so on. Everything before it P divides. That was the reason why we do it. P has to divide all of these. It has to divide B0, B1 up to BR minus 1. What does that mean? P divides this and it divides all of this. Therefore P should divide, but P doesn't divide C0. So what does that mean? It's a prime, right? So yeah, that's a contradiction, right? Because we said that P doesn't divide BR. It was the first time it doesn't divide, the smallest index for which it doesn't divide, divides. Okay, so that's a contradiction. This is a contradiction, and we have contradicted the assumption that P is reducible, hence P is irreducible. Okay, that's the beautiful argument of the Eisensteins criteria. Is that okay? Yes. Okay, so just a small exercise, then we will stop. In fact, there's a nice class of this thing I would have liked to do. I think I will. So let us look at some type of exercises you could do for this. One is, so if we look at 3x raised to 5 plus 15x raised to 4, okay, plus 15x raised to 4 minus 20x cube minus 10x plus 20. Okay, purposely put a polynomial of this type. We can show that this is irreducible using the Eisenstein's criteria. Can you tell me for what P? Why? Yeah. So you look at all of the polynomials. Definitely you don't want anything that divides this, right? And it has to be a divisor of all of them. So in particular, it has to be a divisor of 20. So it should either be 2 or 5, right? So, but 20 doesn't divide, 2 doesn't divide this. So that's why I said you have only finitely many choices in this, just the divisors, prime divisors of the constant. Okay, so you check for 5, 5 divides this, doesn't divide this. Also you need to check that 5 squared doesn't divide this. So it's irreducible. Yeah, that's the Eisenstein's criteria. Okay, another small argument, I'm just going over time slightly. Okay, is it okay? 5 minutes. Okay, so another one is translations. Is it okay? Okay, so translations. So if we look at translations in Z, okay, a polynomial and its translation, so a polynomial will be reducible if and only if its translation is reducible. Okay, it is sufficient for us to just go over the proof in Z or Q. So if P of x is in Zx, for me this is also sufficient, and A is some integer, then P of x is irreducible. In fact, in Qx, if and only if, this actually holds in a more general case, but I'm not too worried about it in the other cases. Okay, if and only if P of x plus A, because this is something that you need to actually define. What you mean by P of x plus A is something that you actually need to define, okay, in general rings. But I believe that we know it in fields which we are familiar with, Q, R, Z. Okay, if and only if this is irreducible in QFX. Okay, so here you can see what happens. You need to expand using the binomial theorem and recombine things. Okay, but so what we can prove is if this is reducible, then that is reducible. If this is reducible, then that is reducible. So if you can write P of x as some Q of x times H of x, okay, in Q, if you can write P of x as some let's say f of x times g of x, okay, the degrees of both of these are going to be greater than or equal to 1, but P of x plus A will be f of x plus A into g of x. I hope you agree with that. Okay, at least over R you should agree with that. You can prove it in more general in other rings, but I'm not worried about it for now. So, and the degrees of g of x plus A and f of x plus A will be the same as the degrees of g and f. The degree of f and f of x plus A will always be the same, right? Because the degree will only come by expanding the binomial, this thing of the first one, x plus A raised to n. So it will remain as n. Okay, these both have the same degrees. Okay, so if you start with so if you say it's reducible here, that means you can write P as f into g. Okay, but P of x plus A will be f of x plus A into g of x plus A. Hence it's reducible there. Now you start with P of x plus A here is reducible here. So you can write this as some f of x into g of x. What will be P of x? F of x minus A into g of x minus A. Right? No? If you start with this is reducible here, that is you can write P of x as f of x into g of x. Then P of x would be f of x minus A into g of x minus A. That would be reducible here. So this is reducible here if and only if it's reducible there. Hence irreducible here if and only if irreducible there. Okay, that's simple enough. And this gives us a nice class of irreducible polynomials called as the cyclotomic polynomials, which is just a second away from a proof. So if P is a prime, then this polynomial, which is a very, very important polynomial, okay, even in field theory, this polynomial seems to be important. So phi P of x equals, this is an interesting one, this is x raised to P minus 1 upon x minus 1, which if you break into this thing, this is nothing but x raised to P minus 1 plus x raised to P minus 2 plus up to x plus 1, right? This is the polynomial, okay? So if P is a prime, then this is irreducible, in Q of x. And the way we prove this is, the way in which we prove this is by looking at a translation. We simply show that a translation of this is irreducible. Okay, so I'm just going to show that the translation of this is irreducible. So let's see what a translation of this looks like. So I'm going to look at phi p of x plus 1, but phi p of x plus 1, okay, I'm not going to substitute it here because that would be quite difficult, but I'm going to substitute it here. That gives us x plus 1 the whole raised to p minus 1 divided by x plus 1 minus 1, okay, which is, this I can open using the binomial, this thing, right, this is binomial expression. So this is x raised to p plus pc1 x raised to p minus 1, right, plus up to plus pc2 x raised to p minus 2 plus up to 1 minus 1 divided by x. This 1 and 1 will get cancelled, okay, we will be left with, and this x you can cancel out, okay, you will be left with x raised to p minus 1 plus this, all you can do as long as x is non-zero, right, you can do all of this argument as long as x is non-zero. If x is 0, then you can check that it works anyway, okay. X raised to p minus 1 pc1 x raised to, yeah, phi p of 1 would be what? So when you put x equals 1, no, x equals 0, you should get phi 1, which is p, I think, right? That should give you p. Substitute 1 over here, what you get? P, right? 1 if you put here, you'll get p, right? Okay, so at the end here you need to check that you get p. That's what I'm saying. Okay, so x raised to p minus 1 plus pc1 plus pc2 x raised to p minus 3 plus up to what was it? pcp minus 1. pcp minus 1 is p, right? P, right? So that would be p. P, right? So this is what you have. Now it is very easy to check that this is irreducible over, yeah. So as I said, when you put x equals 0, you get p. So it satisfies. Even though I have done this manipulation, it still works for this thing. Okay. So now I need to check that this is irreducible. Use the Eisensteins criteria with your prime p. Okay, with your prime p, you can see p doesn't divide 1. Why does p divide all of these? So PCI, when I is less than between 1 and p minus 1, okay, your I is lies between 1 and, so this is going to be p factorial divided by I factorial times p minus I factorial. This product, that is 1, 2, 3 up to p, has a prime p in it. Okay, this is an integer, we all know. Okay, this has no p in it because I is less than p, so it has no prime p in it. Similarly, this also is less than p, so has no p in it, so that p in the numerator will not get cancelled. Okay, it is an integer, but the p in the numerator is not going to get cancelled. Okay, in fact, you all must have done this proof even in number theory. So PCI is a multiple of p. These are all multiples of p. There is a p appearing in the numerator, but there is no p appearing in the denominator. Okay, what are the divisors of n factorial? What are the divisors of n factorial? Not divisors, prime divisors of n factorial. All primes less than n, less than or equal to n. Okay, so p does not appear in the denominator, but p appears in the numerator, hence it will not get cancelled. So this will be a multiple of p. So all these are multiples of p. P square doesn't divide this. That's it. So this is irreducible, hence this is irreducible by the previous exercise. Okay, so that gives you a nice class of irreducible polynomials over Q, called as the cyclotomic polynomials. So we can stop here.